Okay, so we were discussing multicollinearity, the reasons for multicollinearity and the consequences of multicollinearity. So we have understood that the consequences are the coefficients become indeterminate, standard deviations become very large in the presence of multicollinearity, t becomes very small while the confidence intervals, and we also say that was the last point, r square becomes very large. Okay, and t becomes very small. That is, large r square and very small 2t values are also is a symptom that the data is multicollinear or x variables are multicollinear. Now today we will discuss what are the tests of multicollinearity. So the major tests for detecting multicollinearity in the data are: one is Farrar-Globart test, second is Fish confluence analysis, third is you have hygiene values and conditional index, fourth is variance inflation factor and tolerance ratio. So first we will discuss the Farrar-Globart test. So Farrar-Globart test uses three indicators to understand the presence of multicollinearity. One is r square, second is small r, that is r xi xj, and third is standard error of the parameter. So these three statistics are used to understand whether the data is multicollinear or not. Capital R square, that is the coefficient of determination, goodness of it. This is the correlation coefficient between xi and xj, and then the standard error of the regression coefficient. So what is the methodology? Suppose you are having this regression function y as a function of x2 and x3. You are asked to perform all auxiliary regressions. What is auxiliary regression? Supplementary or small regressions of what? These explanatory variables. Explanatory variables have to be regressed on each other. Suppose I will regress x2 as a function of x3, and then I will add x2 as a function. Write once again. Three variables, that will be easy for you to understand. Suppose we have three variables. For generality, we will write this. You have three variables. You are asked to run auxiliary regressions for these explanatory variables. So I can run regression of x1 on x2, then x1 on x3, and then I can add what? These two. Or I can do a regression of x1 as the independent variable, dependent variable, and x2 and x3 as what? The independent variables. Similarly, I can do x2 on x1, x2 on x3, and then x2 as a function of x1 and x3. Similarly, x3 as a function of x1. All supplementary regressions of what? The explanatory variables you are expected to do. And then suppose first time you will be having y data, x2 data, x1 data, and x3 data. x1 is taken as a dependent variable, regress on x2. x1 on x3, then x1 on x2 and x3. And for each regression, find the value of r square, find r of xi and xj, and then find the value of beta 2 hat. So first you will be having single equation model, and when you add additional variable, and once you run this regression, check what is happening to r square, r and beta hat, and then you take the decision. So run auxiliary regressions, find the value of these important statistics, and then you take a decision. So this is the decision rule. If the new variable improves r square without rendering the individual coefficients unacceptable, the new variable is considered useful and retained as explanatory variable. Now you are running x1 on x2, and then you are adding what? Another variable x3. And in that process, if x3 increases or improves r square, suppose here r square was 0.5, and because you have added this new variable r square increases to 0.9, then it means that x3 is an important variable and you have to retain that as an useful variable. Now, if the new variable does not improve r square and it does not affect the values of the coefficient, then that is treated as superfluous and rejected. So, if this new variable x3 that you add here doesn't improve r square and does not affect the coefficients, then you can remove x3. If the new variable affects considerably the signs and the values of the coefficients, then it is considered as detrimental. And if this new variable affects what? The signs of the coefficient and also r square, then that is detrimental. It may be a reason for multicollinearity. That x3 variable can be a reason for multicollinearity. So run auxiliary regressions, and when you add additional variables or you perform another regression by including one more variable, check what is happening to these three, and on the basis of this the variable may be classified as useful, superfluous or detrimental. If it improves r square, you can retain that. If it is not improving r square and not affecting the coefficients, remove that. If it is considerably affecting the signs and r square everything, that is detrimental. There is the chance for the presence of multicollinearity. This is not normally used as a test nowadays because it includes lots of regressions. This you should do, this you should do, the third one also you should do. If you have 4 variables, then single regression, then on 2 variables, on 3 variables, on 4 variables. So the test involves multiple regressions, and hence you are not using this. I am sorry, this test is not called the Farrar-Glover test. This is the Frisch test. I am sorry, Frisch confluence analysis. So this test is called Frisch confluence analysis, and please also remember that it was Rechner Frisch who first used the term what? Multicollinearity. So this is the first test, Frisch confluence analysis. Now and the second test is Farrar-Glover test. Farrar-Glover test for multicollinearity. So the null hypothesis is H0, there is no multicollinearity. H1, the x variables are multicollinear. That is R, xi, xj is 0, no perfect multicollinearity. And here perfect multicollinearity R, xi, xj is equal to 1. So here we use the 3 variable case. Suppose the 3 variables are x1, x2 and x3. Now I am writing it in this form: x1, x2, x3, x1, x2, x3. So as an example, we are taking the 3 variable model, and then this is the case. You have a row matrix of x and a column matrix of x. Now we are taking the product. So how do you take the product of this first row into first column? So that is x1 square, x1 into x1. Second will be first row into second column, x1, x2. Then third will be first row into third column, x1, x3. Then second row into first column, x2, x1. Second row into second column, x2 square. Second row into third column, x2, x3. So similarly you will have x3, x1, x2, x3 and x3 square. Now if this is a row matrix and a column matrix. If you are having an n-dimensional matrix, then you can just put sum over the whole thing. So in a 3 variable model, if you want to find the presence of multicollinearity using the Farrar-Glover test, you find this product matrix of these 2 variables. Now you are asked to divide each of these variables. You are asked to find what is called the standardized variable matrix. To obtain the standardized form, you will have to divide each of these elements by the square root of sigma xi square. So divide each by the square root of sigma xi square. Okay, that is divide the first element by the square root of sigma xi square, and that is the first element should be divided by, or I will write it as sigma xi square x1 square will be divided by sigma square root of x1 square into square root of x1 square. What about the second element? Sigma x1, x2. It should be divided by square root of sigma x1 squared, sigma x2 squared. Okay, yes, that's fine. So similarly, each of these must be divided by the square root of the product, the square term, the square root of the square term. That is sigma x1, x3 divided by square root of sigma x1 square root of sigma x3 square. Now we will have sigma x2 x1 divided by square root of sigma x2 square root of sigma x1 square. This will be sigma x2 square divided by square root of sigma x2 squared into sigma x2 square. This will be sigma x2 x3 divided by square root of sigma x2 squared into square root of sigma x3 square. So this is how you standardize the whole matrix. Okay. And now the third term you can write. I am not writing it. Now what is this? Sigma x1 squared divided by square root of sigma x1 squared into square root of sigma x1 squared. Square root of sigma x1 squared into square root of sigma x1 squared is sigma x1 squared. So sigma x1 squared and sigma x1 squared gets cancelled. We will get this as 1. What is this? Sigma x1 x2 by square root of sigma x1 squared into square root of sigma x2 square. Covariance between x1 and x2 divided by standard deviation of x1 into standard deviation of x2. Covariance by standard deviation is the formula for what? Correlation coefficient. So that's a correlation coefficient between Rx1 and x2. This is the correlation coefficient between Rx1 x3. This is the correlation coefficient between Rx2 x1. This is 1. This is Rx2 x3. So this will be, here it will be Rx1 x3, Rx2 x3, and this will be 1. So this is what the standardized matrix will give you this result. And from this we can find the case of whether the variables are multicollinear or not. How do you find whether the variables are multicollinear or not? If the variables are multicollinear, then you know Rx1, x3 will be equal to 1. So suppose you take the 2 by 2 form. So you take 1 Rx1, x2, Rx2, x1 and 1. So in the case of perfect multicollinearity, Rx1, x3 is equal to, or Rx1, x2 is equal to 1. So that means 1, 1, 1, 1. So what is the determinant? Determinant is 0. So if the determinant of the standardized matrix is 0, then we say we have perfect multicollinearity. And what happens in the case of orthogonality? Rx1, x2 is equal to 0. So this becomes 1, 0, 0, 1. So 1 minus 0 is 1. So if the standardized matrix is equal to 1, then we say that multicollinearity, there is no multicollinearity among the variables. So that's the second test, Farrar-Blocher test. Just write, remember this, you have to find the standardized determinant. For that, take the 3 variables, the row, the column matrix and the row matrix, multiply that, give sigma, and then try to standardize by dividing by the square root of those terms, and then you will get a matrix like this. Then if it is perfect multicollinearity, Rx1, x2 becomes 1. So 1, 1, 1, 1. So the coefficient, the determinant becomes 0, there is perfect multicollinearity. Then if it is orthogonal, it is 1, 0, 0, 1. This is equal to 1. So that is the second test, which is called what is that? The Farrar-Blocher test for multicollinearity. Then the third one, what you have is eigenvalues and conditional index. The third test for multicollinearity is eigenvalues and conditional index. So K is equal to maximum eigenvalue divided by minimum eigenvalue. and conditional index is equal to square root of maximum eigenvalue divided by minimum eigenvalue, that is equal to square root of k. And if k is equal to less than 1000, yes, if k is between 100 and 1000, we say there is moderate to perfect or strong multicollinearity. That is, if square root of k is between 10 and 100. Okay, yes, 10 and it's not 100, it's square root, we will get around 30. Then we will say we will have moderate to strong multicollinearity. If k is greater than 1000 or root k is greater than 30, we say there is severe multicollinearity. That is the third test, eigenvalues and conditional index. So eigenvalues, I hope you have studied where in matrices you say A into what is that? Positive determinators, positive semi-determinant. I hope the rank of the matrix, those things you have studied. I don't know whether you have studied or not, but in matrix you will have to study this eigenvalues. It's a root of the matrix. So please check those things, or if you have not studied, we will discuss when we meet. So please understand the matrix has a characteristic root or an eigenvalue, and A minus lambda I must be equal to 0. That is the situation, and that lambda is called what? The eigenvalue of a matrix. So all matrices satisfy this condition. And if that lambda is like k is given by the maximum eigenvalue divided by minimum eigenvalue, and the square root of k is called the conditional index. And if this k lies between 100 and 1000, we say there is moderate to severe multicollinearity, or strong multicollinearity, moderate to strong. And if k is greater than 1000, we say there is severe multicollinearity. If root k, the root of this will be 10 and the root of this will be around 30. So root k will lie between 10 and 30. It is again moderate to strong multicollinearity, and if root k is greater than 30, we say there is severe multicollinearity. That's the third test, eigenvalues and conditional index. And we have one more test, that's the last test, which is called the variance inflation factor, and a concept which is related to that, which is called the tolerance ratio. Variance inflation factor and the tolerance inflation ratio. So the variance of beta 2 hat is given by the equation sigma squared u by sigma x2I the whole square into 1 minus r23 square, and variance of beta 3 hat is given by the formula sigma squared u by sigma x3I squared into 1 minus r23 square, where 1 by 1 minus r23 square is called the variance inflation factor, and 1 minus r23 square is called the tolerance ratio, tolerance factor. See, you have studied the variance of beta 2 hat, which is sigma square u by sigma xi square. So since it is a two-way, you have having x2 and x3, then the variance of beta 2 hat becomes sigma square u by sigma x2 square into 1 minus r23 square. That's a correction factor, correlation between x2 and x3. Similarly, variance of beta 3 hat is equal to sigma square u by sigma x3I the whole square into 1 minus r23 square. And this 1 minus r23 square is called the variance inflation factor, and 1 minus r23 square is the tolerance ratio, tolerance factor. So these two are the inverse. So inverse of tolerance factor is the variance inflation factor, and inverse of variance inflation factor is what? The tolerance ratio. So what happens now? Suppose there is perfect multicollinearity, then R23 will be equal to 1. What happens here? 1 by 1 minus 1. That is 1 by 0 that is equal to infinity. That is why we say variance inflation factor. So this becomes what? Infinity. The variance inflation. So sigma squared u into 1 by 1 minus r2 squared becomes infinity. Variance of theta 2 hat becomes very large. So when you have perfect multicollinearity, the variance inflation factor becomes infinity. And what about the tolerance ratio in perfect multicollinearity? That is 1 by 1 minus 1, that is equal to 0. So this becomes 0, 1 by 0 becomes infinity. So that's the meaning of variance inflation factor and tolerance ratio. So what are the different tests for multicollinearity? Frisch's confluence analysis, Farrar-Globart test. Third one is conditional index and eigenvalue, and fourth one is your variance inflation factor and tolerance ratio. In the first Frisch's confluence analysis, fix separate regressions or auxiliary regressions, add additional variables, find what is happening to the statistics r square, r xi, yi, and the standard errors of the coefficients. And if the new or the additional variables that you are adding into the model, if it improves r square, use it. If it is not improving it, remove it. If it is affecting r square and the signs that is detrimental, that variable is the reason for multicollinearity. Second is Farrar-Globart test. What do you do under Farrar-Globart test? So what was that which you studied there? The third one is the tolerance ratio. I hope you understood that. Yes, in the Farrar-Globart test, what did you do? You take the three variable case, the row matrix, column matrix, multiply that, standardize it, and then you will get a correlation matrix and what the matrix which is having rxy, rx1, rxi, xj and 1. In the case of perfect multicollinearity, rxi, xj is equal to 1, so the determinant becomes 0. In the case of orthogonality, rxi, xj is 0, so the determinant becomes 1. Third is conditional ratio, conditional eigenvalues and the conditional index. Then k is greater than 1000, severe multicollinearity. K lies between 100 and 1000. There is moderate to strong multicollinearity. And lastly, please do remember, this is used by the packages. Please do remember this formula. Here you will be having x2i and variance of beta 3 x3. That is 1 by 1 minus r23 squared. And you can write that if r23 square is 1, then this becomes what? Infinity, and this is 0. In both cases you say perfect multicollinearity. Then if you are having what? Orthogonality, what do you have? R23 in the case of orthogonality, R23 is equal to 0. So what about variance inflation factor? 1 by 1 minus 0, that is 1 by 1, which is equal to 1. So this becomes what? Sigma square u by sigma xi square. You have now need not include this step. This becomes what? The variance inflation factor becomes 1. You multiply this much by 1. So the original thing you are getting. There is no increase in the variance. So that is happening when there is orthogonality. So you can write these things. So please understand, we have discussed what is multicollinearity, what are the causes of multicollinearity, then what are the consequences of multicollinearity, and what are the tests of multicollinearity. And now we will discuss the last part, that is solutions to multicollinearity. Multicollinearity, that is solutions to multicollinearity. So the most important solution to multicollinearity is to increase the size of the sample. So if you have, see, only 10 observations, y1, y2, y3, etc., y10, if you increase the number of observations, there is a natural chance for multicollinearity to be removed or the effect to be lessened. That's the first one. Second is you can use additional variables in the equation, which is called the simultaneous equation model, which you will discuss in the next semester. That is, there's a chance for you to use what new variables into the equation. Y as a function of x, then you write x as a function of x1 as a function of x2, x3, etc. And then these equations can be estimated together, not by using modulus. And that method is called what? The third one, which is it's called the second method, that is using additional equations in the model. And now the most important method is this one, using the third one is using extraneous information. So using extraneous information means from the theoretical model or from some study which has already been done, you will be able to estimate one coefficient, and that coefficient can be used in this model, and then you can estimate the other coefficient. So extraneous information may be available from economic theory or from empirical studies already conducted. The method through which extraneous information is utilized in order to deal with the procedure of multicollinearity can be done using two methods. One is method of prior information, method of a priori information. Somebody has already done some work on this and you get the result. You use that in order to solve multicollinearity. For example, you are trying to estimate the model yt is equal to alpha 1 plus beta 1 x1 plus beta 2 x2 plus u. Now suppose these two are collinear, x1 and x2 are collinear. So if you run regression, then there may be some problem for this beta 1 and beta 2. Now if by some previous work you are able to get the values of beta 1 or beta 2, then what can you do? You can use what? Then you can use this finding in order to understand what solve the problem of multicollinearity. So suppose by some study you have obtained the value of beta 1 as beta 1 hat. It may be the price coefficient or income coefficient, and you have obtained this. So now suppose you have beta 1, you obtain beta 1 hat from some other study, then you can use this. So I can write it as y2 is equal to alpha 1 plus beta 1 hat x1 plus star x1 plus beta 2 x2 plus u. So I can write it as yt minus beta 1 star x1 is equal to alpha 1 plus beta 2 x2 plus u. So this is already estimated. Now you can find the value of beta 2 hat. So beta 2 hat will be equal to, what is that? You can write it as sigma yt minus beta 2 star x1 into x2 divided by sigma x2 square. So I hope you got, you know how you solve this result. So we have studied this already. So beta 2 hat is equal to, beta 2 hat is equal to, what is the formula? The another formula for beta 2 hat is sigma xi yi by sigma xi square in deviation form. Sigma dependent variable, independent variable divided by sigma independent variable the whole square. That is sigma dependent variable, independent variable in deviation form divided by sigma dependent variable the whole square. So now you get beta 2 hat. So from some previous study you have already obtained beta 1 hat, and you will deduct the y variable of its influence, and then you can estimate the value of beta 2. That is from the method of a priori information. The second method is by pooling cross-section and time series data. Pooling cross-section and time series. Suppose you are trying to estimate the demand function. Okay, dt is equal to beta 0 plus beta 1 dt plus beta 2 yt plus ut. And you know pt and yt are definitely multicollinear. Price will be increasing over time and income will be increasing over time. How do you estimate this? You can estimate this by pooling cross-section and time series data. If you collect data at a particular point of time, you know price will be remaining constant. At a particular point among different individuals, price will be remaining constant. And using that cross-section data, you can first find out the value of beta 1. So using cross-section, find the value of beta 1. And then what you have done there, suppose it is beta 1 hat, then dt minus beta 1 hat dt is equal to beta 0 plus beta 2 yt plus ut. Or you can write this as zd is equal to beta 0 plus beta 2 yt plus ut. Now you can use what you want to estimate the income coefficient. It's a time series data. So in the time series data, what do? You can use the time series to find what the value of beta 2. So beta 2 hat will be equal to sigma dependent variable independent variable divided by sigma independent variable the whole square. That's the second method. So you can use extraneous information. Extraneous information just means you are using some other result in order to find what the coefficient of the variable which is multicollinear. So if you have x2 and x3 and by some other study you get the value of coefficient of beta 2, use that here and then use your data to find the value of beta 1, the other coefficient. Now or you can use in this case as in price, income, etc. You can pull what cross section and time series data and then find the value of the variable. Use cross section to find the value of beta 1, that's the price coefficient, and then use time series to find the value of beta 2. Okay, so what are the solutions to multicollinearity? You can increase the size of the sample. Then second is you can add additional equations into the model. Third one, you can use a priori information either in the form of prior information or in the form of what pooling of data. But these are all what it takes a lot of time or to do some things like this. Normally there are other solutions. You have a factor analysis and what principal component analysis, etc. Factor analysis and principal component analysis, etc. to solve multicollinearity, and this is beyond the scope of your syllabus. So I am just skipping those things, but just when you ask in your exam, you can write to solve multicollinearity. There are other methods like factor analysis and principal component analysis. So please understand. Read the textbook and listen to the class. We have discussed what is multicollinearity, what are the reasons, the inertia concept in economics, the trend factors, and what the presence of lags, what are the consequences. The estimates become indeterminate, standard error becomes very large, higher R squares but insignificant T ratios, wider confidence intervals. What are the solutions? First, confluence analysis, adding additional variables and looking into the statistics. Farrar-Global test, finding out the standardized determinants. Then, conditional index, that's a third one, or eigenvalue, which is greater than 1000 or between 100 and 1000. Then the variance inflation factor, 1 by 1 minus R23 squared, that's a variance inflation factor. And finally, what are the solutions? What are the solutions? Increase the size of the sample, add additional equations, use a priori information, and then other cases like principal components and factor analysis. I hope we will be able to have some physical presence in the classroom, and then if you definitely will be having doubts, we will clear that. And now what I feel is that the portion that is left with me is dummy variables and distributed lag variables. That's what I think. I will have to check those things. Maybe within 2-3 classes we will be able to cover, maybe 3 or 4 classes we will be able to cover those things also. So thank you. So please take additional efforts because I know it's very difficult. So if I use a PowerPoint and just read those things, I don't know how we will be able to understand. That is why I am writing the whole thing so that you can just replay the whole thing and then have an understanding of this. So thank you.